Welcome, teachers. In this explainer, we're going to break down a fantastic method for teaching decimals, all based on worksheet OA. The whole idea is to stop talking about abstract symbols and start giving our students something they can literally see, feel, and hold in their hands.
All right, let's just jump right in with a question that, I'm pretty sure has made every single one of us pause. It's that classic moment when a student with total confidence tells you that 0.14 is bigger than 0.2. We've all been there, right? It's such a common mistake. But what's really going on behind it?
Well, here's what's happening inside their heads. They're not actually seeing a single number, a single quantity. Their brain is just defaulting to what it knows best, whole numbers. So they see a 14 and they see a 2. And in that world, of course, 14 is way, way bigger than 2. And that's the core of the problem we need to solve.
And really, that's the big challenge with decimals, isn't it? Our job is to help students break free from that whole number trap and build a real intuitive sense of what a decimal actually represents as one single unified value.
Okay, before we go any further, a really quick but super important note. The hands-on classroom activity that this is all based on, it uses 4 very specific colors for its paper rectangles. Now, to protect the magic of that discovery for your students, we are intentionally not using those colors here. Think of them as reserved, set aside for your classroom where they'll really build meaning.
So how do we get past that hurdle? Well, the answer is to make it real. We're going to take a material-first approach. We're stepping away from the symbols on the whiteboard, and we're going to build the idea of a decimal from something students can actually touch. The philosophy behind this is something called multimodal anchoring. And don't worry, it's not just a fancy term. It's a really powerful concept. It means we're not just going to tell students what a tenth is. We're going to let them see it as an area, feel it by moving it around, and even think about it in terms of its weight. The meaning comes first. The calculations, they can wait. So let's get into the nuts and bolts. How does this actually work? We are going to build a bridge from the abstract concept of a decimal to the very concrete, very real properties of paper. We'll start with its weight and connect that directly to its surface area. Let's walk through the logic here. We start with a simple fact. A 1 square meter sheet of standard paper weighs 80 grams. Okay. We also know that 1 square meter is the same as 10,000 square centimeters. So with a little bit of division, we can help our students discover that 1 single gram of this paper has to have an area of 125 square centimeters. And that becomes our anchor, our tangible starting point for everything. And this is where it gets so elegant. Once we have our piece of paper for 1 gram, the logic of decimals just unfolds naturally. How do we find the area for a tenth of a gram? Simple. We just divide our area by 10. And for a hundredth, you got it. We divide by 10 again. The physical action of cutting or folding the paper perfectly mirrors the math. It's brilliant. And here's what you get. All of a sudden, 0.1 grams isn't just some abstract symbol anymore. Nope, it's a physical thing. It's this piece of paper with an area of 12.5 square centimeters that a student can actually pick up. Then we divide by 10 again, and suddenly 1/100th of a gram has its own physical identity. It's this smaller piece, this 1.25 square centimeter area. The idea of being 10 times smaller is right there, staring you in the face. It's completely obvious. And finally, we get down to the 1,000th, this tiny little tangible piece of paper. So by building this whole sequence, we've given a concrete, physical identity to each and every decimal place. Which brings us right to the heart of this entire activity, the concrete decimal rectangles. These are the tools that your students are going to make and use. They are the physical embodiment of everything we've just calculated. This is where it all clicks. And this table just lays it all out beautifully. Each of these rectangles stands for a specific decimal unit. Rectangle A is our home base. It's 1 gram. Rectangle B, that's a tenth of that. Rectangle C is 100th, and little rectangle D is 1,000th. The weight, the area, the dimensions, they're all tied together, hammering home the concept from every possible angle. And right here, this is where the real magic happens. This is where we connect the physical objects to the mathematical language. A student holds up rectangle A and rectangle B, and they can see that one is 10 times smaller than the other. This lets them build the sentence themselves. The number that is 10 times smaller than 1 is 1/10. They are creating the mathematical rule from their own direct observation. It's so powerful. So we've seen the how. Now let's talk for a minute about the why. Why is this hands-on material-based approach just so much more effective than diving straight into a number line or a bunch of abstract rules?
Well, the benefits are huge. This whole method anchors the abstract idea of quantity to things they already understand, like weight and area. It just completely prevents that two whole numbers mistake that we started with. It makes dividing by 10 something you can feel. And maybe most important of all, it builds this rock-solid foundation that will support them through every single decimal operation they'll ever have to do.
A quote from the source material really just hits the nail on the head here. It says, understanding emerges from action, from interaction, before any formal calculation. Students are literally building their own understanding by doing, by touching, by playing with these materials. The formal math, the calculations, that can only be built on top of a solid experiential foundation like this one.
And that's really the big idea here. This isn't just a fun activity for a Tuesday afternoon. This is about laying the essential groundwork for their entire future in math. When you invest time in this concrete, physical experience, you are preventing so much future confusion and building a conceptual understanding that's truly built to last.
So the question this explainer really leaves us with is pretty simple. By changing our starting point, by moving from abstract symbols on a page to real materials in their hands, we can fundamentally change how our students see and understand decimals. So, are you ready to help your students build a foundation they can actually count on?